In today's proof without words series, we are going to take a look at three separate geometric proofs of the AMGM inequality. If you do not know what is the AMGM inequality, it just says that the arithmetic mean or average of n non-negative numbers is always greater than its geometric mean. In today's video, we will mainly be focusing on the case of two variables. That is, a plus b must be greater than square root of ab for any non-negative reals a and b. Let's look at our first geometric proof, which was credited to Charles D. Gallen. We have got a semicircle with a big right angle triangle inscribed within it. It is important to mention that the choice of a and b are completely arbitrary. We arbitrarily pick a point on the diameter of the semicircle, and this separates the diameter into two line segments of length a and b. The vertical line through this point forms the altitude of the big right angle triangle subtended by the semicircle. Note also that the big right angle triangle is subdivided into two smaller right angle triangles by its altitude. We note that the radius of the circle is a plus b divided by 2, given that the diameter is a plus b. On the diagram, the altitude of the right angle triangle is labeled as having length square root of ab, but this has to be proven. To prove this, we label the length as m, and start off by doing some angle chasing, labeling the angle over at the down left corner as x, so the other angle of the triangle will be 90 minus x. After we do this, we can obtain the angles labeled in blue for the adjacent right angle triangle, using the fact that angle subtended by the semicircle is 90 degrees. The fact that both the smaller right angle triangles colored in green and magenta share all three same angles mean that they are similar. This implies that the side lengths of the triangles are proportional. From this, we obtain the relation a divided by m equals m divided by b, and so m equals square root of ab as desired. Finally, we just need to observe that the altitude of the big right angle triangle colored in blue is always lesser than the central radius, which is denoted by green. So we get the relationship square root ab less than a plus b divided by 2. Equality happens when the two lines coincide, which is when a equals b. Our second geometric proof deals with a series of four interlocking rectangles, each of which has side lengths a and b. The first thing which we do with the diagram is to annotate all the side lengths which are not included in the initial diagram. After this, we can see that the grey quadrilateral in the center of the diagram is actually a square with side length a minus b. The area of the small square in the middle corresponds to a minus b square, while the area of the entire big magenta square is a plus b square. Subtracting the first term from the second, we see that the leftover is 4ab, contributed by the four rectangles, each of area AB. Now, you might say that this equation is self-evident by just expansion, but I guess this sort of defeats the purpose of proof without words, as we would then have no need for the diagram at all. Anyway, after this, we can divide the equation throughout by 4 and derive the inequality a plus b divided by 2 square must be greater than ab. Taking square root is the last step, which gives us the expression we desired. In the case where a equals b, the inner square will have an area of 0, and so the inequality becomes an equation. Now we can move on to our final and third proof. In the diagram, we see two circles next to each other. One circle has diameter a, while the other one has diameter b. Therefore, the line segment in red has length a over 2, and the line segment in blue has length b over 2, each of them being radius of the circles, and this gives a combined length of a plus b divided by 2. By taking the difference of radius between the two circles, we further derive one of the side lengths of the triangle to be a minus b divided by 2. Finally, we can apply Pythagoras' theorem to the right angle triangle in green to see that the other side length is square root of AB. If you are wondering why we know the triangle is a right angle triangle, note that the horizontal line at the bottom forms a tangent to both circles, and hence the angles circled in red are all right angles. The bottom side length of the green triangle is parallel to the tangent by construction, and so we must have a right angle triangle as well. The justification is all that we need, since the conclusion automatically follows when we compare the lengths in a right angle triangle. The hypotenuse, which has length a plus b divided by 2, is the longest side, and so must be greater than the side length, which has length square root ab. Equality happens if and only if a equals b, in which case we have two circles of same size. I hope you have enjoyed these nice proofs, and I will see you in the next video.